people don't even realize, or we seem to have forgotten how valuable structured data is, because it's kind of the ground truth of the business, and it captures the blueprint of the business, and we seem to have forgotten all that. And we are now excited about answering questions about documents.
Now, this is a bold claim, being able to create machine learning models faster and better. What is this? Break that down for me a little bit more.
Yes, I can give you an explanation, right? If you think about how we are building, let's say, these predictive machine learning models today, right? These models would be, let's say, churn models, recommender systems, any kind of risk scoring models, fraud models, across all kinds of industries, from hospitals to social media to manufacturing to supply chain optimization and so on. The way we are doing this is, right, that fundamentally these models use the internal data that is usually structured in tabular form, right? It sits in some database, in some data warehouse. It usually has this relational structure. You have multiple tables interlinked with primary foreign key relations, right? So it would be a user table, a product catalog, a record of all the orders of these users, maybe the table that includes all the website behavior, so all the clicks that says this user clicked on this web page at this time, and so on, right? And
all the features.
we want exactly, right? So this would be the data, and the way we build these models today is that we would basically now be joining these tables, generate features, and then train our favorite neural network or whatever it is on this data. And I can go deeper what I mean by all this, but basically it takes us, I don't know, several months to build these models. We need to engineer the features. Features need to be up to date. They must not be stale. There is this time travel issue. We then put these models, let's say, in production to actually run more than just in our private notebook, and that's another can of worms and so on. But if you look at what's kind of been the trend in AI, let's call it this way, right? The trend in AI has been, let's learn on raw data. Okay, so in big revolution in computer vision was, let's not feature engineer from the pixels in the image, let's train a neural network directly on the pixels. Okay, and we get these super great neural networks for computer vision, total revolution. Now we are in the age of large language models, right? In the old days, when we did, let's say, natural language processing, natural language understanding, even if you think when, IBM won Jeopardy, the competition, it took 300 people, 2 years, and a bunch of very careful feature engineering so that computer was able to answer Jeopardy questions and be better than humans. So in some sense, we had AI at that time, but it was just kind of hand engineered, right? Today, transformers they just learn over a sequence of tokens, and it's they learn over raw data. So what the interesting thing is to ask, okay, so it seems like that the world of machine learning, let's say, predictive modeling, has been stuck in the past. We don't learn on the raw data. We learn on this featureized data. So what I was very excited about was to say, okay, how could we change this? How can we develop methods that can learn directly on raw data? And the hard part here is that your data in machine learning does not come from a single table. It comes from multiple tables, right? So
and it's usually very messy too, right? It's usually
exactly.
not pristine data that gives you a clear story.
It's not pristine. It has missing information and all that, right? So what we have developed is a set of neural networks, and I can talk about them. They are basically based on graph representation of the data that allow you to learn directly on the raw database data. So they allow you for the first time to learn over multiple tables at once. And now, because of that, you completely sidestep the feature engineering process, which means you save humongous amount of time.
And compute.
And compute maybe not so much, actually. You need GPUs because these models are now a bit bigger. So you need to train on GPUs. But the computer works when you sleep. So it's very fine. But there is another benefit, which is because now the neurons are learning how to combine the data. the fidelity, the nuance of those learned signals, it's much, much higher, so your models get more accurate.
Uh-huh. So now I've heard folks talk about recommender systems with LLMs and just basically the inherent understanding that LLMs have. You can suggest certain things to an LLM, and it's going to be able to have a better view of what a user will want. Is this kind of what you're talking about, or is this a whole separate thing?
I would say it's a separate thing, right? Like if you want through LLMs with for recommendations, it kind of works okay. It's not super terrible, but it's not good either because it's all kind of based on some kind of common sense. It's not really learned from the data for your specific users, for your specific understanding, and so on. And I can give you a simple story, for example. I was chief scientist with Pinterest for 6 years, right? Took Pinterest from 100 people to post IPO. And I built a recommender system platform there, 3 generations. And what was, for example, a super hard problem with Pinterest is that as you see these images, maybe you have an image of the rug on the floor and you have an image of a tapestry on the wall. They practically look the same. The neural network could not tell the two apart, but humans could. And the behavior on those things was very, very different, right? So at Pinterest, we very quickly realized it's not just enough to treat a user as a sequence of, let's say, a sequence of images they visit, because the neural network would get confused. What you need to think of it is basically you need to think of Pinterest as a set of interactions of users with content and think of that as a graph. So if you say, oh, if I interact with this image and then other people interacted with it as well, and then I kind of know what this image is about, right? This tapestry can say, oh, I'm interacted with other tapestries. So I'm a tapestry. I'm not a rug on the floor. And a rug on the floor says, oh, when people click on me, they also explore other things that very much look like rugs. So I know myself, right? I'm not a tapestry. I am a rug, right? Like
It's guilt by
and this kind of
association.
sorry, it's guilt
It's
by
guilt.
association.
Yeah.
Exactly. And this is what these kind of graph-based approaches allow you to do, because they allow you to kind of learn from this structured relational information. And this is what sequence models will miss.
And if I'm understanding this correctly, for example, when you're doing the traditional machine learning models, you're really optimizing for one or two things. And with what you're proposing now and what you've built, does it have a more holistic view? Like if we have the two extremes where you have traditional ML models and then the other extreme is a large language model, where do you fall on that spectrum?
That is a good question. So the approach we developed, it's called relational deep learning, and it can take any database, represent it as a graph of relations between the entities in your database, and now you just learn over that graph of relationships. And if you now train a transformer-like architecture that is called a relational graph transformer that does not attend kind of over the tokens like a typical transformer, but attends over the tables of that schema of the database, you can do both. You can train small task-specific models, kind of. You can think of them as kind of classical machine learning models, but now really learned directly from the raw database data. But you can also learn a large pre-trained model that is good at any task on any database. So like if you go to ChatGPT and ask it, hey, do time series forecasting for me, or you go and say, hey, I have this transaction, how likely it is to be fraud? You will get terrible results, right? How would ChatGPT know the likelihood of a particular transaction being fraud? It won't, right? But the large pre-trained relational graph transformer, which we call a relational foundation model, allows you now to ask this type of questions without any model training. So maybe the point is the same way as in, let's say in biology, we accept that we need a DNA foundation model. We accept that we need a protein foundation model because protein is not natural language. I think the key thing we need to accept is that for structured data, we need foundation models trained and built for structured data. We cannot textify a database, throw that into an LLM, and hope it will work, because it does not.
Okay, so I'm starting to understand a bit more of the picture of what you've built. And now can we get into the nitty-gritty of how this actually is built and what you're doing? Do I just throw in my database and then do I need a whole ton of data? Like what does this look like in practice from how I interact with it or how I train a model that is now going to be one of these types of models?
Yeah. So the way you need to do is you need to, let's say, first select the tables, the schema you want to learn over. Um, Usually, it's 5 to 50 tables. And what you need to do, you need to specify what are the primary foreign key relations between these tables, right? That user ID in this table is user ID in that other table. Um, and you select kind of the semantic types of columns. So there is a bit of, let's say, data registration, data modeling, even you can call it data preparation step. But it's very small because you just need to say, this is my schema, here are the relationships. And after that is done, you have two options. One option is that you use now the large pre-trained model, that you just point to this collection of tables, you prompt it with a specific predictive question, and half a second later, you will get an answer that is on average as accurate as a manually built model that takes, I don't know, a month to build. What you can also do is then to say, okay, I am going to fine-tune my model for a specific task and for a specific database, and then you can fine-tune, and that will get you to superhuman performance, right? Because now you have specialized the model for specific database, for a specific task. And of course, if you are, for example, doing fraud detection, which is a high-value task where you truly care about, the last bit of performance because it's saving you so much, let's say, money, then you wanna train a task-specific model. If you are in a more of a regime where you want to do basically almost like ad hoc querying, ad hoc predictive querying, you would use a large pre-trained model to do that.
And on these task-specific models, do you see folks creating an ensemble of models, just like you would maybe in the traditional fraud detection use cases?
Not really, not really. What we basically see is people training a single model that then learns how to attend over all these, let's say, different data from transactions to locations to time and all that, and combine that into the best possible predictive signal. Right? That's the difference. Is if you think about maybe a fraud model. In a fraud model, you say, okay, I have a customer. How many transactions did they do last week? And you create a feature. And then somebody, some other data scientist wakes up and says, it's not number of transactions last week, is the number of transactions in the last, 10 days. Great, let's add one more feature. Then somebody else wakes up and says, no, I know the answer. It's how much you spend in the morning. And I define morning as, 6 to 9 a.m. And let's add that counter there. And then somebody else wakes up and says, hey, but there is daylight savings time. We just changed the clock in US. Okay, so in the summer, this is the morning. In the winter, that's the morning. But you see my point. Kind of the point is that it gets we are computing these arbitrary statistics over the data to be able to say, okay, how much did this person purchase in the last time period? But if you have the attention mechanism can attend over each individual transaction, so it can learn to combine them in ways that humans will never will. And that's why it's able to kind of extract more signal from the raw data than, a SQL query or a manually defined feature will, because the neurons can do so much more, and they are basically trained to combine the data together, if that makes
It's
sense.
Yeah, it's basically like move 37 in the Go. That how in Go how what was it? It was Move 37, right? I think it was somebody will have
Exactly,
to fact
exactly,
check.
exactly. It's maybe something like this. It can be counterintuitive. It can be something that is very fine grained. It could be some, second order correlation that you as a data scientist, as a machine learning engineer, never put into a feature and things like that. And because of that, it's, I would say, the same intuition as in computer vision, right? In computer vision, we are like, oh, here's the edge, here's the gradient of color. Nobody's doing that anymore. It's just the neural network figures it out how to combine all the pixels to say what's in the image. And basically, we do the same, right? We take the database, represent it as a graph, and then the transformer architecture, the graph transformer architecture, learns how to combine all these pieces of information into an accurate prediction. Rather than, what is done today with machine learning, which is you manually figuring out how to combine transactions into something that allows you to predict something about the user.
Yeah, so you're wiping away all of that feature engineering. What are us data scientists and machine learning engineers going to do now?
That's a great question. I think it's exciting. I think it's good because you're not a feature engineering machine. Right? It's almost like saying, "Oh, you brought me a robot that helps me sweep, but I want to be sweeping the floor all the time." No, right? Like you are here to build models, to have impact on the business. You're not here to clean data and feature engineer, right? Those are the two most boring parts of your job. So what we see, for example, is that this really kind of opens the data scientists to be able to build models faster, to really focus on modeling, to focus on what should we be even predicting, right? You never in let's say in business, in enterprise, there is never a predictive problem that is given to you. It's a business problem that is given to you. So how do I go from a business problem to a predictive problem? Asking yourself, what is even predictable? What is modelable from my data, right? Because, you know, garbage in, garbage out. So what we see is then, because now let's say the feature engineering step, you don't need to worry about. You are much more worrying about what's the raw data, how is the raw data structured, what is the information flow over the raw data, and so on, right? And maybe let me just say this because I get asked many times. People say, "Oh, is this AutoML?"
Uh-huh.
Right? Like, remember this old
Yeah.
AutoML promise, right? It's what was AutoML, right? AutoML is you run a gazillion of SQL queries against your database. You join every table with every table. You aggregate everything 7 different ways. You create these humongous, silly feature vectors. And then you train a bunch of models and hope it will work. Right? So it's like kind of throwing spaghetti against the wall and hoping that something sticks. What I'm talking about is fundamentally different. It's a single neural network that has the ability to learn, to attend over the collection of tables, and you are now training or tuning this neural network on that collection of tables. So it's faster. It scales to the largest use cases in the world. I can say more about that later, um, and it gives good performance.
Well, one thing that is very clear after hearing this is the value of that raw data, as if we didn't know that already, right? But how much can you have messy, ugly, shitty data and still get value from this method, basically?
That's a great question. So here is what I would say. In some sense, quality of the data matters, but because these models are learning from the entire relational structure, they can implicitly impute missing labels. They can correct for mistyped or misentered information. Even if the linking information is a bit noisy sometimes, the models can recover from it because they're kind of learning holistically across the entire relational structure. So another place, for example, that this is important if you think about cold start problems, right? Cold start in a sense that, let's say, maybe in the recommender systems and so on, or you have a new user, you have a new item, you haven't seen anything about it. But then you have an old user or an old item that a lot of others have already interacted with, so you are very data rich, information rich about this item. What is the benefit of these models is that they can kind of trade off. If the item is new, they will focus on the attributes of the item, properties of the item, I know, description, image, and things like that, and they'll latch on that. But as soon as that item starts getting connected into the graph by users interacting with it, buying it, and so on, now the model is starting to use this relational structure, what you kind of said earlier, like the guild by association, to say, okay, who is interacting with this? What else are these people doing? Let me give an accurate recommendation. So, it allows you kind of, or the models learn how to trade off between learning from attributes to learning from structure. Just it leads to very robust models. That's all I wanted to say. Both in terms of missing data, data ugliness, as well as robustness.
Do we need to have super clear ontologies and a knowledge graph set up, or is that something that it infers also?
Good question. I would say somewhere in between. All we need to know is what table links to what table. Many times we can infer this automatically from column names. And that's about all we need. So the model does not rely on semantic information, right? The model relies on patterns in the data. So maybe here is the difference is that the model learns how to recognize the patterns in the data to make those predictions. So we don't need a super rich semantic model. We don't need to explain what is the true meaning of every column to the last detail, because from the kind of the patterns from the past that predict the future, that doesn't matter so much.
So talk to me about scale.
Scale. Good question. So this scales to tens, 100 billion nodes. So for example, I can tell you, maybe to illustrate, I can tell you some examples of how this technology runs in practice and who's using it. Okay. So one interesting story was, a few years back, DoorDash came to us, right? DoorDash during COVID was growing great, right? Everyone was ordering food, but post-COVID, kind of, right? So they came to us and said, "Hey, can you help? Can this technology help us?" So we looked at restaurant recommendations, right? So recommend a restaurant you are going to order from next. In particular, recommended problem is recommend a restaurant you never ordered from before. So it's try something new. And the way this gets surfaced to you is through notifications, right? You get a notification saying, "Hey, do you think you want to order from this restaurant today?" Right? And this is one of the core problems at DoorDash, right? So they've been kind of using traditional technology to build these types of systems with the best possible people and so on. We trained our transformer model over a collection of tables. It was a 30% increase in accuracy, 30.
Wow. So me as a user, when you suggest a restaurant for me to try, it's much more pointed and it's much more to my liking.
Exactly. It was much more pointed. It was much more to my liking. And that resulted in several hundreds of millions of more purchases or orders on DoorDash, right? So it was humongous business impact. Right. So that's just one example, right? And now you say, what's the scale of DoorDash? Is, I don't know, several 100 million users. I don't know, hundreds, billion orders, all the website behavior, all the searches, all the geographical location, all the cuisine information. So it gets quite interesting as well. That's, for example, one example where we saw like this humongous lift in performance over a flagship model, right? Something that is not one data scientist woke up and said, "Oh, can this do better?" No, it's like a team, several years of effort. It can do better. I can give you another example that's even larger scale, and this is in advertising.
Oh, before
Yeah.
On that DoorDash one, how long did it take to go from inception to production with that?
One benefit of these models is because they run on the raw data, putting them in production just means refresh the raw data, right? So for people who have put models in production, like just having that feature store, having up-to-date features, making sure features are not stale, productionizing them, babysitting those workflows is like, babysitting a 2-year-old kind of, tantrums all the time, right? Like on call all the time. So it's very hard, right? But here it's much easier because you just say, here's my fresh data. Make predictions on it. You refresh the data, make predictions on it. So we put that in production, I would say, quite quickly, maybe a few weeks. And of course,
And
that was a set of...
it's irrespective if the data schema changes. As long as you refresh the data, even if the data schema changes, you're still able to infer the right things.
If the data... So the models themselves allow for data schema changes. So it wouldn't be a problem. But if you would, let's say, drastically change the schema, change the composition of tables, you would, let's say, retrain the model that takes maybe a couple of hours, and now you're back in the game.
Yeah.
Right. So that's one benefit. Another benefit is if you think about user behavior changes all the time, right? Or if you think about fraud, right? Fraudsters are always inventing new ways to commit fraud. And we as data scientists, we are always a step behind because we are like, oh, my model performance is deteriorating. I need new features. But with this approach, you're just, let me retrain the model, and the model will figure out the new signal, and so on. So it's also much easier to keep up to date. You can automatically retrain and really get the most value out of the data you have.
Okay. It makes a lot of sense. So yeah, what's the other scale? The massive
Yeah.
scale one that's even bigger than DoorDash.
What's bigger than DoorDash? I can talk about this one. It's advertising models, right? So this is the bread and butter of the internet industry, right? It's like predicting how likely is a user to click on an ad, because every time you visit a website, there is a prediction for this user. What is the most likely ad they are going to click on? That ads get put in front of you. If you click it, the advertiser gets paid. So no click, no money. Click, you get money. Right? So 1% lift in accuracy of this predictive model means 1% lift in your revenue. So the use case here is Reddit. And Reddit has advertising models running on their website. And, it's bread and butter of what they do. And every, single or tenth of a percentage point matters a lot in terms of absolute revenue. So there, I can say they usually increase the accuracy of the model by 1 to 2% year over year. And with this approach was like 5 years worth of improvement in accuracy. In a month or something, right? Again, over this flagship model that's been tuned and, the latest from research incorporated and so on. And I think this just shows kind of the power of this, just let the neural network learn over the data, right? The trick is the data is split or sits in multiple tables. So you need now a generalized transformer architecture that can attend across the tables and learn how to extract the signal automatically rather than us humans doing it manually.
Yeah, I was talking to my friend Sid at Anthropic, and he was saying that they have a saying internally, which is let the model cook.
Basically, exactly. And I think my point is for natural language human-like tasks, LLMs are great, but LLMs totally fail on structured data, right? You cannot take a database and JSONize it, put it in a big blob of JSON, put that as a prompt and say, now based on this, give me a prediction. What will the user like?
Do you see this working for time series also?
I see this working for time series a lot as well. Exactly. There are two ways to think of time series, right? One is just to say, oh, I have an individual time series, I have a sequence, and I predict the next token. So people have been, I would say, quite successful training sequence-based transformers on time series data. Our approach is a bit different because the way we think of it is it's not one time series, it's a graph of time series, because these time series are usually connected, through maybe you have a sales record for one product, but products are related to each other, or maybe they are I don't know, sold in different stores and things like that. So by representing this time series as a graph, you actually get a further increase in performance, because the model does not only learn how to make prediction from the single time series, but also learns how to attend across other related time series to better forecast, right? Because some time series might have different legs, some products might be correlated, some stocks might be correlated, and things like that, right? So predicting from a single time series is very hard because you don't have that information. But through this, let's say, graph-based approach, you can learn to borrow information from other related time series, which again leads to the increased performance, increased
Yeah, it
accuracy.
feels like you're just giving a much richer picture for the model to understand.
That is a great way. I think that is a great way to say it, right? You give a much richer set of information to the model, and then you give the neural network the freedom to combine this information in the best possible way for that forecast, that prediction, that risk score.
Hmm. Another thing that I'm thinking about is, does it take a team to make this happen? Or is this something that it's like, how many people, how many resources, if I wanted to try and do this at my company tomorrow, what am I looking at actually like needing to dedicate towards this?
That's a great question. What we see is that with this, you need about 20x fewer resources than traditional approach. So it means you can do much more with a much more leaner team. You still, let's say, need a data scientist or someone who kind of understands predictive modeling, but that person can build, you know, 10 models in a single day if they like to do so. And then what you also need, I think, with predictions, it's always important that you are able to plug them into whatever product, whatever decision making you are doing, right? So predictions are only useful when you are making decisions, when you are taking some action based on that decision. So we need some engineering resource that says, okay, now that we have prediction, here is what we are going to do with them.
Yeah, it's still the model building and then putting the model into production. It's just that the model building piece has been drastically cut.
Exactly, or the model, the time to build a single model has been cut, which means as a data scientist you have much more time to explore, to kind of really think about how am I modeling this business problem, what is the best way to model it, what is the most accurate way to model it, and allows you to kind of to explore that space much more efficiently and faster than with, let's say, traditional feature engineering that takes so much time.
Yeah, and I can't stop thinking about how two of the main feature stores have recently gotten bought or acquired for, like Tecton got bought by Databricks recently, and then I just heard Featureform got bought by Redis. And so it feels like that whole paradigm, was it maybe a dead end? If we can do things faster this way, why wouldn't we?
That's a good question. I think this feature engineering approach to things, you know, uh, it got revolutionized first in computer vision, then in natural language, but kind of it felt like that, machine learning, predictive modeling was kind of stuck in the past. We were doing the same thing for 30 years, right? Like we were putting data in a single table, and then, we were training decision trees, and then we were training support vector machines, and then, I don't know, logistic regression was fancy, and then neural networks were fancy, but it was all trained on this single table. And all these feature stores were built because of that need to to kind of compress the data or join the data into a single table. I think with this new wave of kind of bringing AI to machine learning, yeah, the need for that is drastically reduced. Um, and we see it both in terms of productivity of building these models, we see it in building more accurate models, and it just simplifies the stack. right? It's actually the statistics from industry is staggering. You need about 2 full-time people per model. Okay, right? So companies, if they have 10 models in production, they have 20 people taking care of them. If you want 30 models, you need 60 people. If you want 400 models, you need 800 people. And that's the ratio. It's like 2 people, you need 2 full-time employees to babysit a model. And 30% of the model cost just goes to maintenance of running that model. Of course, then what also happens is, people change jobs. So what happens is that in reality, you have all these models running in production that somebody built who's no longer with the company. Nobody wants to touch those models because as soon as they, even look at them, those models are going to break. Nobody knows what to do, right?
Dude, it's even worse than that. I remember back in the day, we had somebody come on here and they were working at Yandex. And they said, yeah, my last 6 months there, I had to go and get rid of a bunch of zombie models that were just out there. Nobody wanted to touch them because nobody knew if they were making the company any money at all. And people were afraid that, well, if we take them offline and it did turn out to be one of those models that was making the company model or making the company money, that could be a really big problem.
Exactly. I think this maintenance and tracking of these models is a huge problem. But with this, let's say, neural network technology, with this relational deep learning graph transformers, it's much easier to maintain. It's much easier to audit. It's much easier to have them there to retrain them automatically and take care of them. So the maintenance cost becomes much less.
Well, and speaking of maintenance, if you're talking about the feature store, feature engineering way of doing things, a lot of the maintenance would just happen with the feature pipelines. And that, I know so many folks who had headaches because of that. And keeping the data fresh is not as simple as it sounds.
Oh, it's super hard, right? Like it's super hard. Actually, it's super hard, right? Even if you think about, basically it means that for almost like if you have these counters, these features, right? For every event, you have to update your features. So whenever you make a transaction, your feature needs to be updated. If it's not updated, it's stale and it's old information. And if you made a bit of mistake and updated it a bit too far in the future, then you are kind of having information leakage, time travel, and your models are no good. So it's in reality a super big problem that I think people in research or academia, we don't really appreciate that because the data is always just given to us. Here's a training set, here's the test set, it's a fixed split. Who cares? You can kind of pre-compute it all. But in reality, just updating those features is a huge pain.
Yeah. Well, this is fascinating. I mean, you've gone from computing features to just training these models. How many GPUs do I need to train a smaller model? Maybe take me through if it was fine-tuned to if I wanted to just build my own foundational model. What am I looking at as far as compute needs, costs, and then also time? Because if you're training a
Uh,
large language model, you need like a month and a half type thing.
it's actually interesting. Um, the big surprise is how little resources you need. So it's actually very cheap, especially if you compare to large language models, then it's really cheap. Large language models are really humongous. They kind of read the entire internet and memorized it. To do predictions, you don't need to do that. You need to learn how to recognize historical patterns and how those predict the future. And that seems to require much less parameters. So these models, you can do well with 50 million parameters, which is peanuts. You can do well with 100. Um, and if you want, you can train a billion parameter model. But those are super tiny when we think of LLMs. So what does this mean? Is you need less resources. Training times are in hours, not weeks or months. And very importantly, when you put things in production, they are actually sustainable, right? Putting LLMs in production is kind of many times unsustainable because it's too expensive. Each LLM call is just too expensive. But with these types of models, because they are smaller, actually they are quite efficient to run. So your compute cost is low, and there is then the benefit. It kind of, the cost benefit analysis actually works out well. So you don't need tens of billions of parameters. These models can be actually quite small from that point of view, and you can train them on a single GPU. Now, if you want the foundation model, maybe you need a couple of GPUs, but not 10,000.
Yeah, we don't need to build a data center to
Exactly.
train this model.
Exactly. One thing I wanted to say is that these structured data foundation models, as we said, are smaller than large language models, easier to train, have less parameters, and this also means they are cheaper to operate. One thing that is maybe fascinating here to me is that you can actually build a pre-trained model that allows you to kind of answer tasks ad hoc. You don't have to even fine-tune. You don't have to kind of train for a specific prediction task, but you can almost give a set of training examples in context to the model, and the model is going into a single forward pass, make you an accurate prediction, if that makes sense.
And do you interface with these models through prompts like you do with large language models?
That's a great question. So if you have a pre-trained model, the way you interface with it is through some kind of prompting. It's a domain-specific structured language we call predictive query. And it basically has two parts. It has a predict part, and the for part. Predict says, I want to predict this quantity for this specific entity. So you say, I want to predict your purchases next week. I want to predict some of your transaction values next month. I want to predict probability of fraud for this transaction. So you specify that, and yeah, this is basically almost like a prompt, and based on this, the model is then making a prediction. If you are talking about a general foundation model, if you fine tune, then the model just takes the data and gives you the prediction you want.
So it's not like I'm using SQL or Python.
It's not like to prompt the model. You are using almost like SQL, where you specify what's the quantity you want to be predicted.
Yeah, it's
so
like
that's how you would be
pseudo-SQL.
prompting this. Pseudo SQL,
Yeah.
sure. It's a SQL that selects over the future that hasn't yet happened. So you need to predict that future.
Nice. And you said something in a talk you gave that I wanted to dive into more, which I found fascinating, and it was agents need predictive AI tools. Can you break that down for me?
Maybe to start at the beginning, right? Like, why are we making predictions? Right? We are making predictions because we are making decisions based on those predictions, right? Why am I predicting fraud probability? Because based on that fraud probability, I decide whether to stop a transaction or not. Why am I predicting churn probability? Because based on that estimate of churn, I'm then taking some action to bring that customer back, right? Why in a hospital I'm predicting surgery readmission probability? Because based on that, I decide whether to discharge the patient or not, right? So if you think in finance, you could say, okay, why am I predicting your probability to default on a loan? Because then I decide, do I give you the loan or not, right? So prediction is really a basis for decision making. So if now we believe in autonomous agents need to make decisions, right? And you don't make decisions based on common sense, right? It's okay. It's not terribly wrong, but it's not optimal as well. You want to make decisions that are rooted in the data. To make decisions that are rooted in the data, you need to kind of predict the outcome of those decisions, right? And right now, what's the bottleneck in, let's say, deploying this type of autonomous agents is their ability to make decisions. And this means that now you have your beautiful LLM agent, super intelligent, and then you have to build manually some machine learning model that's going to say, oh, what's the probability of churn, right? Because imagine a simple agent that says, let's go identify people that are most likely to churn. Let's identify the best offer to send to to each of those people. Let's write a nice personalized email and send it out. Right? In this workflow, there are two big decision problems. Which people are likely to churn? What is the best offer to give? And those are two predictive tools that you need to solve this use case end to end.
Damn, I see where you're going with this. That is
So agents will
wow.
need predictions. Maybe we have not realized that yet, because what agents do today is they query some document database and retrieve a couple of passages. But those are not real agents, right? A real agent is actually something that does something to you, right? Like, or imagine I'm a customer support agent. I want to estimate what's your lifetime value, what's your probability of churn, because based on this, I will talk to you very differently. I will give you different offers. I may suggest different remedies. Those are predictive problems, right?
So how can we leverage the predictive models that we've been doing, but like you said, make sure that they're faster?
Exactly. I think the benefit is in basically using relational foundation models that these LLM agents can use as tools to query for these predictions. So whenever you show up, they're like, how likely is this person to churn? What is their lifetime value? Oh, now that I have these estimates, this is what I'm going to do. Right? What's the next best offer to give to this person? I'm making this decision on the fly based on a predictive model that is rooted in my data that gives me an accurate prediction, rather than use some kind of common sense hallucination to say, oh, what shall we do here?
Yeah, or rather than how it's been done right now, which is that we're creating these predictive models, and maybe there's some advanced teams that are offering up these predictions to the agents. But as we just have been talking about for the last 40 minutes, that is a cumbersome process the way that we're doing it right now.
Exactly. That's the alternative. It doesn't scale. It means you have to hire 2 humans for every predictive problem you have. And that's a lot of humans to hire.
It's so obvious. Like, why don't we have that right now? Or maybe you've seen some teams that are actually doing this because, like you said, the step A, step B, step C is a super common use case. And it's a pattern that happens within companies every day. Have you seen agents being used like that? If not, yeah, like what is the blocker?
Yeah, I would say we have seen agents being used like that, and we have a couple of clients deployments where this is happening. I think the blocker right now, as I see, is the knowledge, right? It feels like there is this mm, AI delirium out there, and then there are all
Tell me
these
about
kind of quiet people who are doing real work, and they are not being heard, and that seems to be kind of a big disconnect to me.
Is there anything that I didn't ask that you want to talk about?
That yeah, there is actually hope for machine learning as well. That right now is a bit on a side track, or people don't even realize, or we seem to have forgotten how valuable structured data is, because it's kind of the ground truth of the business, and it captures the blueprint of the business, and we seem to have forgotten all that. And we are now excited about answering questions about documents. But I think the world is going to come back, because enterprises are here to make accurate decisions, to make business impact, and to drive the business forward. And for that, you need prediction.